hide there when the place was closing, so I could see it. Yeah. Yeah.
I just saw
it. Well, it's, yeah, they were my friends and my dad. My dad loved it.
Oh my god, he's the one that like,
I have any questions?
Yeah, him, my friend, and me, yeah. We always, every time we went, we would try to hide.
Do they give you your own hotels?
Oh yeah. They check everything. They have to check everything.
You can type in flights overhead and it'll tell you what planes are overhead. Oh, really? Yeah. I don't know what's that. It's like, what do they consider overhead? So kind of like, well, it tells you like the direction.
I don't know how to say this. They were hiding out on top of Sawyer's Island.
That thing, every time we get on there, it's
9 miles from the plane. Southwest Airlines.
One of them.
That thing has, every time I go there, it's gotten more and more. I didn't know what to do.
Like, never know how to swim.
Apparently not.
That's what
I
it
don't
works
know.
That's like not even that
It's
far.
like, yeah, exactly. Yeah. I don't know. Is it even that deep?
Probably not. Like, probably
Like, I'm
even
wondering how I read it somewhere. Yeah, it does what I thought. But there is that big boat in there, so I don't think it would.
Alright guys, so number 19 from the book. Let's try to do this one. Instructions say find the volume again. Because they could give me, I want you to realize, if they wanted me to integrate a function over this, it would just be one extra step for the function they give me in the interval. So that doesn't really matter. What really matters is setting up the limits. In this case, the function is going to be 1, because they just want the volume of this thing, right? But the whole purpose of this is to get practice getting the limits correct. And then you can throw whatever function inside that they want. It's going to be some density function, or whatever the function is. Might be some electrical, whatever, like the one they had about the heart. So the wedge above the xy plane forming the cylinder, x squared plus y squared equals 4. So that would be, you know, it's got a circular base and it goes up. Cut by the planes equals 0 and y equals negative z. That's this dude here. So can you draw, which region would you consider my inputs to be then? Which plane would my inputs live in? Is one way to look at it at least. And another way to look at that is, what's my roof over my floor, right? What's going to be the roof that's sitting over the floor? The floor would be the region of my inputs. The roof would be the function that sits over them. What does it look like? Yeah, because it would kind of suck to try to do it in any. This actually sits in the xy plane already, so sort of a giveaway. And all the points that are here actually go to some output, right? In this case, it's going to be that plane sitting overhead, right? So then I want the xy plane. So can you guys draw the trace of this in the xy plane? Try to draw that. I want the trace of this in the xy plane. Be very careful. Don't draw too much. I only want the trace of that region that exists in the xy plane.
You like a top circle or something? The C.
Could be, yeah. Be careful about where it actually is. Which half of the circle are we talking about? x-axis here. It goes from what to what? Yeah, -2 to 2. And it's kind of a giveaway. The z's are positive, and since y equals -z, the y's have to be negative. So it's got to exist down here. You can kind of see it from the picture. Kind of turn yourself around and look at it like that. It's below, right? So now it's going to go how far down here? That's the interesting question, right? Well, it's got to go to where? Yeah, because now on the y-axis, it'll go to -2. So here's my semicircle there. That's my region we're talking about. So this is kind of there's a definite way that I'd prefer to do this. Which variable do you want to allow to be from a number to a number? Meaning the other one's going to be from a function to another function. Or another way to say it is, which way do you want to draw your arrows? From here up or from here over? Yeah, up. I'd much rather go up. Because if I go over, this is one function and that's another function. Right? That's the bottom half of something, that's the top half of something. That sucks. But this is much better. This goes from this function to 0. It kicks ass. So while x goes from -2 to 2, so now we figured this out. I want to do dy dx. The outermost is x. It's the one that is allowed to go from a number to a number. Any specific, now to figure it out, pick an x. I don't care where. It's going to have to go, y is going to have to go from this to 0. And of course, what is this? Yeah, exactly, 11. And of course, the easy part is what is, well, maybe, let's see. What is z doing?
Z is going from 0 to
Yeah, beautiful. Z is going from 0 to -y. I love it. Right? So z is going from 0 to -y. Because they tell me z goes from 0 and y equals -z, which means that z equals -y. That's the definition of that roof. Now again, I mean, very often we'll think the roof is always the thing that's up here, like the z piece, but sometimes it'll open sideways. But to me, this just kind of makes sense. That's the roof that's over this thing, right? That's the thing that's going to go on the very inside. And then I want to integrate over the floor that go up to the roof. I'm not sure if this imagery is working. We'll see. Whatever, dude. It's another word for floor. It's good. So what's got to go on the very inside? Again, unfortunately, 1. Yeah. And then you can integrate that. I mean, how would this work? Let's actually try to do this interval. What do you get in the very innermost piece here? Z, and then when you evaluate it from -y to 0, you get -y. Cool. Try to take the next couple steps on that. Double check, you have your x dependence captured by your dx. That's inside, so it looks good so far. Everything's contained. Nobody can escape their d variable piece. Here, what do you get? You get negative 0 minus negative 4 minus x squared over 2, so you just get squared, of course. So 4 minus x squared, square root squared is just 4 minus x squared over 2. So there's a minus there, so your minus negative that becomes positive that. Right? And then to do this integral is easy. Now that's 2 minus x squared over 2. So when you integrate that, you get, what do you get? You write this again.
2x.
2 minus x squared over 2 dx.
X minus x over 6.
I like it. So you get 2x minus x cubed over 6 from negative 2 to 2. And you just plug and check. You go to town. I was a little worried that a few people on the test were putting the limits in the wrong order. That should be second nature. Right? Put this in first. So 4 minus 8/6 minus negative 4 plus 8/6, right? Negative 2 cubed is negative 8 minus is plus. So you get 4 plus 4 minus 8/6 minus 8/6. You get 8 minus 8/3. 16/3. Notice real quick, watch. Little funny thing about if I had something minus that same thing thirds, this is 3/3 of it, minus 1/3 of it is 2/3 of 8. 2/3 of 8 is 16/3. Right, so it's a nice little trick. It happens often enough, trust me.
Wait. You get 16/6. How do you get 8/3?
Because that's what 16/6 is. Yeah, you're right.
Really?
Divide by 2. Reduce it.
Oh.
You're fine.
Okay.
All right. And really, they have a few problems where you have to integrate and they have little functions inside finally. Not just, oops, let me unfreeze. Why they have little functions inside, not just ones. So that'll be a little more interesting. Okay.
Why do you change around like the order?
Not in this problem here. I gave you one problem where they ask you to change the order of integration. So I'm going to kind of let you guys, just to give you a little hint, you might want to draw some traces and maybe even get some isometric paper and draw in 3D what that region is. Okay? Have faith. All right. Because I really need to get into this section here. And just to let you know, just to remind you guys, 13.6 is extra credit. And I'm seriously considering doing the same thing with 13.7. 13.7 is one that's very often skipped. I didn't want to skip it, but maybe I will. 13.7 has to do with a lot of matrix algebra. Right? There's something called the Jacobian that you use a lot in linear and sometimes in differential equations. And I feel that this might be a little too early to get into anyway. So what we're going to do today, in the little bit of time we have left, is to try to get into some different coordinate systems. And the first one's kind of nice. The first one is very simple. The better you understand polar, the more sense cylindrical coordinates will make. Because all cylindrical coordinates does, polar lives in how many dimensions? 2. All cylindrical does is it says, let me just add z on top of it, just like we do to x, y, add z. Well, r theta, just add z. That's all it is. Because how do you define a cylinder? You define the circular base, which is polar, and then the height, which is z, which is still the old holdover from Cartesian. How are we doing so far? Semi-understood? Where it gets more interesting is when we start saying, maybe I can define things in terms of 2 different angles, and that'll be spherical. So for right now, What's that?
This is 13.5.
Yeah, 13.5, yeah. So all cylindrical does is we still have r and theta, but now we just add in their z. Just to remind you guys, and again, to show you what happens most often, you'll get something like the inner integral would be like this. Would be dz. And the outer integral has got to be over a region. But who remembers now what the outer integral in this case for cylindrical coordinates going to be? What units are they going to be? Not units, but what variables are they going to be over? What type of? Yeah, theta and r, right? So who remembers what dA was for polar coordinate system?
RDR.
I like it. So the true integral is going to be f dz r dr d theta. Now, if you put that r inside the integral, does it change anything? No, it doesn't. Right? It's just put there just so we understand that this is actually goes together. It's a stupid little r that messed some of us up on the test. You can't forget that little r to go there for polar. Okay. But besides that, there's nothing much new here, truly. If I want to do a problem here. It takes them forever just to talk about what it's going to look like. So if I had a problem like this, that looks delicious. And I want to change the coordinate system. I want to use cylindrical on this, and you can call it. You can kind of see why. It's got a beautiful little x squared, y squared in there. Everything. The nice thing is it does truly just add z on top of everything else. So x is still r cosine theta. Y is still r sine theta. Z is z, yay. Right, because it's just saying we're going to use the z that you guys use. So obviously, one thing is how many coordinate systems exist? As many as there are people that want to make them. You can make up your own coordinate system, I don't care. How many main ones exist? Depends on who you talk to, really. There's like 8 main ones that I've used, but I've seen other ones that people use. And they're all going to have these little translations normally from Cartesian to them, to go from what we're really used to what we're using, right? Cylindrical obviously works best when you have inputs that are polar, and the inputs that are circular, right? Because the base of a cylinder is going to be circular, so they work best when you have inputs that are in the circular region. Or you have a function itself that's best expressed in polar coordinates. Okay. So this problem here is a good example because it's got, kind of looks like one we did earlier too. So to convert this over, I need to graph. First, I want to draw a sketch of the region of inputs. Right? This here is nice and easy. The z is just -1 to 2. And it's going to stay that. My z stays the same. But what do my region of inputs look like? So x is going to go from what does x do? X goes from 0 to 2√2. Cool. And what's y doing at the same time? Yeah, and of course, what's the radius of this? This is just a little circle, right? If y equals square root of 8 minus x squared, you get this circle. The radius, of course, is going to be that. That's where that came from, really. So if x goes from 0 to 2√2, y is going to go from the bottom part to the top part of that semicircle. pretend like that's symmetric. So that's what my region looks like, right? This is the problem that was on the test, not really, but it's sort of like the problem on the test where you want to first get the region as is given, now take that region and define it in terms of r and theta. Don't try to translate from what they give you. No. This is now easy to relate to in terms of r and theta. What's r?
2 square root of 2.
Yeah, it goes from 2 square root of 2 is what r is overall, and so it's going to go from 0 to 2 square root of 2, right? And what's theta doing? I like it, negative pi over 2 to pi over 2. Shoot. So now to rewrite this, here's dz, r, dr, d theta. Theta is from negative pi over 2 to pi over 2. R is from 0 to 2 root 2. And what's z doing? Negative 1 to 2. You gotta love it. Now what's the function look like now?
1 plus r squared.
I like it. Cool. I like it. There you go. All right. That wasn't too bad. And what makes it a lot easier than what you think it is I don't have to relate directly to this crap when trying to translate. I graph the region this describes, and then I go straight from here to polar. It's a lot easier to give me a circle, and let me go to polar. So let me first draw what circular region I'm talking about, and then go straight to polar. And now this actually is, eventually that r is going to help me out. Do you guys see that? The first integral is easy. That's a constant, so I get z times this crap, and then I just go from negative 1 to 2. Thank God that r is there for the second integral, so I can do what eventually? U sub. I got a u equal r squared that's stuck inside, whose derivative is basically this, minus the 2. I don't care about constants. I can bring them in whenever I want to. Yeah.
So we don't multiply r right away?
No.
We wait until
You could. It's kind of silly. I could just take that r over here, because in terms of z, it's a constant. It's not going to change anything. So if you don't like that, put in the r like in the middle of things. You can always just put the r, attach it right to this, because the first integral you're going to do doesn't care. It's like, whatever. I can take this whole damn thing out of here and put it over there. dz doesn't give a crap, right? Because it's a constant according to that integral. I can move constants inside and outside of integrals. Cool. Okay, and they try to graph it for me here at the bottom. A little disgusting, that's all right. So I'm going to let you guys go through some of these examples on your own, but they're pretty straightforward, actually, thank God. The better you know polar, the better there's going to be. Just a little preview. And some of you guys don't want to hear this, maybe. But there's a whole reason for me to put that submarine problem and the reason. Do you remember the submarine problem?
Oh no.
Oh, calm down.
Probably don't do it.
Calm down. Because here, real quick, before you leave, spherical coordinates. Who remembers the trick that everybody didn't do on that problem?
Horizontal multiplied by sine of
You had to do like a double trig function, right? Because you had to break it up first according to on the surface, and then you had to break it up from there. So what we do in spherical coordinates is going to be a lot like that. Instead of r, we use rho. A little more formal, so it makes us realize, oh crap, we're in a more formal coordinate system, not just tacking z onto this thing. It's rho. So rho is going to be just like r. It's going to be any direction though. So if rho equals 7, that would be the sphere of radius 7. Because now rho is like r's big brother. He's in the third dimension. So x is going to be, let's start with z actually. If rho is the distance out to some point, theta is the same as it always has been. Theta is going to be this angle here. And the new thing, the brand new thing, because rho isn't really new, it's just a different name. The brand new thing is going to be this angle here, phi. And phi is the angle between the z-axis and the line that I'm talking about, the position vector for that point. You see that? So I certainly could tell somebody, all right, turn this way, Now turn that way. Now go this far out. That's basically what this is doing. Turn that way. That last one is going to be that angle that takes me out of the plane. Right? So in this case, Z is going to be how related to phi? This is where things get a little interesting.
Looks like it's cosine.
Rho cosine.
I like it. So Z is rho cosine phi. Do you guys see that? Z's got to be rho cosine phi. So both of these are going to have that sign. You guys remember that? So rho sine phi is going to sit in the xy axis. Now how do you break it off between x and z? Well, x is going to be this business times cosine theta. Y is going to be this business times sine theta, because cosine goes with x, sine goes with y. Whoa. And the really cool thing, and that's all I'm going to talk about today, but when we get back into it next time, is I'm going to show you how the integral looks disgusting when you just look at it, but I'm going to build it off of the polar one we did before. Just add one more thing on top of that. Okay.
Just let me know when I go.
Right there.